If you haven't done so yet, please pause the video and try to answer this question on your own before listening on. One of the keys to understanding this question is that this parallel plate capacitor can be modeled as two capacitors that are arranged in parallel. So if we were to draw that situation in the traditional manner, what we could do is display this capacitor in the following manner. And this capacitor on the left-hand side would be this section of the original parallel plate capacitor. And then this capacitor on the right-hand side would be this section of the original parallel plate capacitor. And we know that the equivalent capacitance of two parallel capacitors is simply the sum of their individual capacitances. So if we could come up with an expression for this capacitance as well as for this capacitance, all we would have to do is sum them together, and that would give us the equivalent capacitance. Now, of course, we'll note that the capacitor is filled with a dielectric material. In fact, it's filled with two different dielectric materials. And we know that the capacitance of a parallel plate capacitor, when it is filled with a dielectric, is equal to its regular capacitance, which is a constant multiplied by the area of one of the plates divided by the distance between the two plates, multiplied by the dielectric constant, or kappa. And as noted, this parallel plate capacitor has two different values of kappa, kappa 1 and kappa 2. So what we're going to do is take this expression for the capacitance of a parallel plate capacitor that is filled with a dielectric, and we will insert it in for both C1 as well as for C2. We'll just make sure that for C1, we'll call the dielectric constant kappa 1, and for C2, we'll call it kappa 2. Now, as far as the area is concerned, if we look back at the original picture, we can see that the area of this plate right here is A divided by 2, and the area of this portion of the plate is also A divided by 2. So we're going to actually substitute an A divided by 2 for both of those areas. And if we look carefully at this expression, we can see that we can factor out a greatest common factor of epsilon times the area divided by the distance d. We can see that that term is present here as well as in here. Epsilon times the area, all of that divided by d. So let's factor that out. And then what we're left with after factoring out that GCF is kappa 1 over 2 plus kappa 2 over 2. Of course, we can simplify that as just kappa 1 plus kappa 2 all divided by 2. And at this point in the problem, all we have to do is plug in the known values. Remember that epsilon has a value of 8.85 times 10 to the minus 12. The area is given to us, but it's given to us in a non-standard unit of centimeters squared. So we're going to have to convert that into meters squared. And one way of doing that is to remember that 1 meter is equivalent to 100 centimeters. But because we want to cancel with centimeters squared, not just centimeters, we would have to square this result right here. And so when you multiply that out, you would get 5.56 times 10 to the minus 4 meters squared. So that's the standard unit for the area. And then also the distance is given in a non-standard unit. That's a little easier to convert. All we have to do is multiply that by 10 to the minus 3. And that'll get it into meters. And the kappas are given in their standard unit. So let's go ahead and plug everything in. So after plugging in and working that all out on your calculator, you should get roughly 8.41 times 10 to the minus 12. And then the standard unit of capacitance is farads. So this would be the correct answer to the question. Thanks for watching. If you liked the video, please click the thumbs up and also subscribe so you could stay tuned for other videos. Remember that you could send in your own question to the email address on the screen, and I'll do my best to answer it on YouTube.